Listo, ya estamos en vivo.
Gracias. Welcome to the Tartaglia seminar. Today's speaker is Neil Mañibo. Neil obtained his PhD in 2019 by Bielefeld University. Afterwards, he has held some postdoctoral positions at both Bielefeld University and the Open University in the UK. He has done some research on automatic sequences and the generalizations, number theory, among other topics. Today, his talk is titled Diffraction and Aperiodic Order. Please welcome Neil Mañibo, and let's give him a virtual applause. Thank you.
So thank you very much for the invitation and for that very kind introduction. Very happy to be here. So today I will be giving a talk on diffraction and aperiodic order. In particular, I'll be talking about aperiodic tilings and what does it mean to get the diffraction of an aperiodic tiling. So there are many different notions of spectral theory, and I will be talking more about the one that's connected to measures, so to more harmonic analytic objects today, which is, of course, it necessitated some formalism because of Shechtman's discovery of quasicrystals. So we first start with what it means by to have a diffraction pattern. So physical diffraction means that we have a material or we have an obstacle which we subject to some radiation. So on this slide, I have two examples. So the one on the left is optical diffraction, wherein you have slits or you have obstacles and you let laser pass through it with a series of lenses. And because of the slits or because of the obstacle, the laser will be diffracted in different directions, and then these will be allowed to propagate until it hits an opaque screen. So when it hits an opaque screen, the constructive and destructive interference will show in what we call the diffraction pattern. So the peaks there are actually the intensities of the light, and we'll see that in a diffraction pattern you may have bright spots or dark spots depending on whether you have constructive or destructive interference. So that one, the one on the left, has been known before the 1900s. Now, people have wondered whether it's possible to use crystals or solids as obstacles for a diffraction experiment. And the problem back then is that the spacing between atoms is not compatible for diffraction if you use visible light. So laser or light in general has too long a wavelength for it to diffract a crystal. So what Lau and his collaborators discovered in 1912 is that one can use electromagnetic radiation which has shorter wavelength, namely X-rays, to use a solid as a diffraction grating. So here's an example of a diffraction pattern which they got from subjecting I think it's copper sulfate, so subjecting a solid under X-ray. So here you can see that the dark spots, they represent positions where you have high constructive interference. So it means that you can characterize a material using non-contact methods using diffraction. So as I said, we want to look at diffraction of aperiodic tiling. So before we proceed on discussing how we can get or how we can view tilings as models of solids, we define what a tiling is. If for those who are not familiar with it, so we first define what a tile is. So it's just a compact subset of R with non-empty interior, and a tiling is just a union of tiles which covers the space. In our case, it's RD. So it covers the space. So it means that it's gapless and that there are no overlaps, which means that the interiors of the corresponding tiles are all empty, or have empty intersection, pairwise intersection. An example of this is the well-known Penrose tiling, which Penrose discovered in the early 70s, and which is also one of the first examples of a tiling which is aperiodic. It covers the plane, but in a non-periodic manner. As you can see, it's also obvious that this tiling has five-fold symmetry. And it's very important to note that five-fold rotational symmetry is not compatible with periodic structures. So if you have something periodic mathematically, it means that it sits on a lattice. But if you have a lattice in 2 or 3 dimensions, the only rotational symmetries allowed are 2, 3, 4, and 6. So 5 is not allowed. And it's actually an easy exercise in linear algebra to show that five-fold symmetry is not compatible with the lattice structure. So if it's not a crystal, if it's not a lattice, physically it means it can't represent a crystal. So before Shechtman's discovery, a crystal means something with periodic structure, because a crystal is one where if you subject it to a diffraction experiment, then you can see this clear spots in its diffraction pattern. And people back then, they thought that could only happen if you have something which is periodic. But so I said that Penrose had that tiling in 1974. So Alan McKay, who was back then in the UK, gave it to one of his colleagues and said, okay, I have this atomic structure that sits on the Penrose tiling. Can you do a diffraction? Can you check what the diffraction pattern of this tiling is? And his colleague, who was, I think, in Cardiff, used this an actual optical interferometer to check that, and he got this picture from that specific solid derived from the Penrose tiling. So as you can see, this has bright spots similar to the spots that Lau had obtained for the X-ray diffraction. The only difference is in this case, this is of course with lasers, so you really have bright spots now representing constructive interference. But the pattern is this: the pattern of having bright spots is analogous to what they saw in 1912. So they thought it's not possible because only crystals can have a diffraction pattern like this. And it didn't take long before Shechtman, actually he already discovered it in the same year, but was able to publish it 2 years after, that indeed there are solids which are not periodic but still have Bragg peaks in its diffraction pattern. So the Bragg peaks are the points with high intensities, and they represent some sort of order in the material. So this work of his not only revolutionized what people thought of as a crystal, but also gave birth to the new mathematics, or the new field of mathematics called aperiodic order. Because now it's clear that there are other objects which give pure point diffraction or Bragg peaks in the diffraction, which are not periodic, and it's one of the mathematical aims of aperiodic order to characterize those with that kind of diffraction. So I told you that they did they come up with a model of a solid from Penrose. So one way to do that is to look at the tiling. So given a tiling in 2D or 3D, actually in any dimension, you can look at the vertices, and we know that we don't have overlap, so the vertices or the location of the vertices are well defined, and you can view it as a location of an atom in your space. So in this case, it's a 2-dimensional tiling. You get a 2-dimensional model of a solid. Note that this assignment is not the only possible way of deriving a point set from a tiling. It's also possible that you can choose the interior or a point in the interior of each of the tile and just make choose the control point in such a way that it's consistent with the geometry. So if it's rotated, then the location of the control point must also be rotated in some way. So this is a way to get a point set from tilings. And so here's an example of or a picture of a simple diffractometer. So what you have is a laser here, and then you have here a lens and a slide where you can put your gratings which represent or which encode an aperiodic tiling. So here, for example, there are 6 different gratings where each contains a printed version of a tiling in a very small scale. So remember, the wavelength has to match the spaces of points here. So these are very the spaces between points in these slides are very small. And what you do is you can put it, turn on the laser, and project it to a wall, and then you will see what the diffraction pattern is. So I'll show you later what an actual picture of the diffraction for Penrose is using this setup. So now there are many ways of how we can get a tiling which is aperiodic. But one way, or one famous way of how to get them, is using substitutions. And the reason why this is very beneficial for people looking at aperiodic order is that substitutions are they're very structured. They have a very clear hierarchical structure that allows one to examine the model or examine the tiling in different scales. So we begin with something which is familiar with people working on symbolic dynamics, namely the Fibonacci substitution. So by the way, a substitution is nothing but a rule that sends a letter into a finite word or a word of finite length over a finite alphabet. So in this case, our alphabet is going to be composed of 2 letters, A and B. And the Fibonacci substitution sends A to AB, and it sends B to A. So it's a well-known fact that to this rule, I can associate a combinatorial object, which is called the substitution matrix. And what the substitution matrix encodes is that it encodes the number of letters present in the image of the substitution for each of the letters. So each column represents the image of one letter. So for example, the first column represents the image of A under raw. So what do we mean by 1 1 here? Because A is sent to AB, you get 1A and 1B. And then the second column represents or corresponds to B, and it reads 1 0 because in the image of B, I have 1A and no B. So it encodes the combinatorics of your rule. So a standing assumption for substitution is that we normally assume that it's a primitive matrix. It means that there's a power, a positive integer, such that m to the n is a positive matrix. Now, if you have primitivity, then you get from standard Perron-Frobenius theory that this matrix admits a unique eigenvalue of maximum modulus. In this case, it's 1 plus square root of 5 over 2. And to that eigenvalue, you get an eigenvector, a left eigenvector with strictly positive entries. So I wrote here that it's an like lambda, the dominant eigenvalue is going to be the inflation factor, and L is going to encode the tile lengths. So it already alludes that I want to associate a tiling to the specific substitution. What I meant by tile lengths is that lambda and 1 are going to be the natural lengths assigned to A and B. So here, one can also talk of a bi-infinite fixed point of the substitution or a power of it. Namely, if you start with AA, with this finite word AA, I can apply the square of the substitution and I can get ABA, because A is sent to AB. So A will be sent to AB and then B will be sent to A. So under the square of the substitution, A will go to ABA. But note that what it does is I get that AA I get AA in the middle after iteration and get longer and longer parts, which extends to both directions. Which means that I can do this process, I can iterate it infinitely many times, and I can get a bi-infinite word that extends to both directions. So here what I get is a word over my alphabet, A and B, which extends to the negative integers and the positive integers. In the next slide, we show how to get tiling out of this bi-infinite fixed point. So I told you that the matrix allows one to get geometric data from the substitution. So here, you remember the rule before, A goes to AB, B goes to A. Now I just replace all A's by a tile of length lambda. In this case, that's going to be the red tile. And the blue tile is going to be the B tile, which is now of length 1. And this is what we call the Fibonacci inflation. And the reason why it's an inflation rule is because under the inflation rule, each tile gets inflated exactly by lambda. So this is lambda plus 1, which is lambda squared, and gets subdivided depending on the rule, depending on the original substitution rule. So this is still A goes to AB, B goes to A. And under one step, each tile is expanded exactly by a factor of lambda. So now I told you about this symbolic object, which is the bi-infinite fixed point of my symbolic rule. What I can do is just replace all A's by a red tile and all B by a blue tile. So if I do that, what I get is what I get here is a tiling of R, or is a tiling of the real line with two different tiles, the red tile and the blue tile. And from this tile, I can also associate a point set by just collapsing each tile to the location of its left endpoint. For example, I have this red tile at the origin. I'll just put a red circle at 0. And that's going to be a point in my point set. So one can now view this third object as a mathematical model or one-dimensional mathematical model of a quasi-crystal. Now composed of two different atoms. So you have a blue and a red atom, which might correspond to two different atom types. So that's normally how one gets from a substitution to a point set, which is now our model for the solid. Well, of course, in higher dimension, you bypass this moving from symbolic to the geometric picture because the geometry is already given. So an example of an inflation rule in 2 dimension is the Goodrich-Lanson-Biot tiling, which is generated by this rule. So you have the same rhombi from Penrose, but the inflation rule is now different. And this is the tiling that arises from this inflation rule. As you can see, it's less ordered as opposed to the Penrose tiling. I mean, it still has 5-fold symmetry. Maybe you can't see it here because I specifically chose a patch which doesn't show the 5-fold symmetry. But compared to other patches of to most patches of Penrose, it's very disordered. And we'll see later that this actually shows up in the spectrum. So the inflation factor for this tiling, we'll go back to this. It's equal to this value of lambda, 5 plus square root of 5 over 2. And I just want to mention in passing that this is a non-piso number, which is also going to play a role later. So now we already know how to get point sets from tilings. Now to do diffraction, we have to view these point sets as measures in RD. And from this measure, we derive other measures which will represent the diffraction pattern that we see if we do this laser experiment. So I wrote here that the diffraction theory of point sets, it involves harmonic analysis of unbounded Radon measures. So what's a Radon measure? So a Radon measure on on RD or in general on a locally compact abelian group is a complex valued linear functional on the space of compactly supported continuous functions. So what it does is it picks, so for any function which is compactly supported and continuous, it assigns a complex number. So that's what a random measure does. So now we want to build the measure that corresponds to our solid, right? So the one-dimensional example that I showed from the Fibonacci substitution is going to be a point set in R. And by point set here, I mean that it's going to be a countable union of singletons. So we let lambda be a point set in RD, and we let Wx be the weight associated to the point X, which lies in the point set. So normally, for diffraction, if you have finitely many atom types, you just let W depend on what kind of atom it is. In that case, for the Fibonacci example, W only depends on whether it's an A or a B, whether it's a red tile or a blue tile. Now, what you do is you build this what we call Dirac comb. So it's going to be a measure supported on your point set, and it's weighted depending on your chosen weight of your chosen complex weight vector or function. So this W just distinguishes different atom types. So this now models your atomic distribution. Now, from this, we can compute its corresponding autocorrelation. It's going to be a volume average convolution. So here AN is it's an averaging sequence. I don't want to go too much detail, but you can, so for RD, you can look at AN as balls of radius n and then growing and growing balls. So we look at the restriction of the measure on a finite ball, and then we convolve it to its twisted version. So what we have here is going to be a finite measure. So this in general is unbounded. This is an unbounded measure. But this on the right for the autocorrelation is going to be a finite measure. And the autocorrelation is going to be a limit measure of finite measures, which are averaged with respect to a nice averaging sequence. And then the diffraction is going to be the Fourier transform of the autocorrelation. So not all measures are Fourier transformable, but in our case, autocorrelation is a nice enough measure. So it's a positive definite measure, which means that it's Fourier transformable. And in fact, its Fourier transform, which is gamma hat, is going to be a positive measure. And positive means that it admits a unique Lebesgue decomposition. So we know that if we have a positive measure on RD, then it admits the decomposition to three parts, namely the pure point part, so PP, the AC part, which is absolutely continuous part, and SC, which is a singular continuous part. So we want now to study, so the goal of mathematical diffraction theory is to study these three components given given mu. So, but first, before going to methods on how to study them, let's first try to see what they say about the measure. So the first component is called the pure point component, and this is a component that's supported on a countable set. So the support of this is a countable set, and it's the mathematical or the analytic counterpart of Bragg-Peaks. So this is an actual picture of the diffraction of the Penrose styling using the diffraction setup that I showed you before. So this is an example of, or a picture that shows the pure point component. In fact, we know that for the Penrose styling, the two components are absent. So it's purely, well, it's purely pure point. And the presence of such a component is attributed to having long range order in the material and it's also connected to almost periodicity. So mathematically, we can write this, we can write the pure point component into another Dirac comb, which is, so IEP now corresponds to the intensity, so how bright the points are. And then L star is the support of your measure. So in this case, the location of the points here, you take the union of them, it's going to be L star. And it's usually called the Fourier module. So the rule of thumb here is that if you have a material and it gives rise to something with pure point diffraction or with a pure point component, then it has some sort of order. Now you go to the second part, to the second component, which is the absolutely continuous component. So before, the measure is supported on a countable set. Now this measure is supported on sets of positive Lebesgue measure. So it assigns to subsets of RD of positive Lebesgue measure some non-negative values. And this is the analytic counterpart of diffuse diffraction. So diffuse diffraction is something that you have if you have an amorphous solid or something which has less order than that of a crystal or that of a quasi-crystal. And normally, also in dynamical systems, the presence of absolutely continuous components suggests randomness. So the material is less ordered. So mathematically, one can write the absolutely continuous component as a Lebesgue measure times what we call a radon-Nikodym density, phi of k. So phi of k is a locally integrable function in RD. So this is a closed form for the absolutely continuous component, and it's very useful. It's very useful because there are renormalization equations that transfer to each of them, and that it's inherited by this function here, which allows one to investigate whether or not this component is present. And we'll go to that later. So lastly, we have the third component, which is a singular continuous component, and it's supported on the complement of the supports of the previous two components I mentioned before. So it's supported on Cantor type sets, namely sets which are uncountable and are of zero Lebesgue measure. They're very difficult to detect in experiments. So if you normally do a diffraction experiment, it's very hard to say whether what you see is actually singular continuous or AC. Pure point is much it's much convincing. Like if you see it on a diffraction pattern, you can pinpoint it right away. But these two are normally very difficult to distinguish. And this describes the regime between order and disorder. So an example would be the two-dimensional tiling I showed you before, which is composed of the two types of rhombs from Penrose, the thick and the thin rhombus. It's actually from a paper by Godrèche and Lanson. And in this paper, they did numerics for that tiling, and the diffraction pattern for that tiling looks like this. So it's more cloudy than the one you get for. So if you go back to the Penrose picture, this is clear that these are actually bright spots. Whereas here you also get tenfold symmetry, but it's more cloudy than the one we get for Penrose. And so in 1992, they conjectured that this is actually singular continuous, but they weren't able to prove it. And using the method that we'll discuss next, we were able to show like 3 years ago that this is actually the case, that their conjecture is actually true. So now that we understand better what the three components are and what they say about the underlying atomic model, the goal is to understand what the implication is of the properties of the substitution say about the individual components of the diffraction. So if I give you a substitution, under some mild assumptions, you can get a tiling. And from a tiling, you can get a point set. Now, the question we're posing here is, what properties of the substitution have explicit implications in the spectral type of the underlying measure. So two questions which are natural along this vein is, so first, when is gamma hat equal to gamma hat pure point? So that means that when is it the case that the two components are actually absent? So there's no AC part, there's no SC part, so no continuous spectrum. And one is actually connected to one of the biggest conjectures in the field, namely the piso substitution conjecture. So the conjecture states that if you have a one-dimensional substitution, well, you build the matrix, right? And then you look at the eigenvalue of the matrix. So you have two assumptions. You first assume that the characteristic polynomial of the matrix is irreducible, and that the lambda is a piso number. So piso means that all of its algebraic conjugates are inside the unit disk. So they have absolute value, or they have modulus strictly less than 1. And the piso substitution conjecture states that if rho is a primitive matrix, primitive substitution which has irreducible characteristic polynomial, then its diffraction is pure point if and only if lambda is piso. So this is still an open problem. So we can ask a weaker question. And the weaker question is that it's the second question. So when is the absolutely continuous component absent? So we do not require that both are absent. Maybe there's some SC, there's some singular continuous spectrum, but when can we guarantee that the second component is not there? And to do this, we have to look at more particular properties of the substitution that does not rely just on the eigenvalue lambda. So a way to do that is via Lyapunov exponents. So what we do is now I'm going to look at the square of the inflation rule that I showed you before. So remember before I had red goes to red, blue, blue goes to red. Now this is just a second iteration of that rule. And to this rule, I can assign another matrix which does not just encode the number of tiles present in the super tiles. So these are called super tiles. It doesn't only count them, it also encodes the location of the specific tiles. So this new matrix is what I call a Fourier matrix. So to this inflation rule, I can associate a Fourier matrix, which now encodes the position of the super tiles, of tiles in the super tiles. So for this specific example, the associated Fourier matrix has trigonometric polynomials as entries, and it's parameterized by a real number. So the idea is to encode the positions using exponentials. Note that if you set k to be equal to 0, it gives you the classical substitution matrix of the inflation rule. So if you plug in k is equal to 0, this is going to be 1, 1, 1, this is going to be 2. So you get the substitution matrix of this rule. But so this has more characteristics of the inflation rule. So now the question is how to get B out of the rule. So if you look at the squared inflation, you look at the positions of the tiles. So for example, the red tile is located at the origin. This blue tile is located at position tau. This should be lambda, but tau here is also the golden ratio. And the red one, the last red tile is at position tau plus 1, because this is of length tau. Sorry, this is length 1, and this is of length tau. Likewise, for the super tile corresponding to B or to blue tile, this is at position 0, this is at position the golden ratio. So same thing. So the first column corresponds to the super tile of type A. And the second column corresponds to the super tile of type B. So if you look at the first column, the reason why I have 1 plus e to the 2 pi I1 plus tau k here is because I have two tiles which are both red and are at position 0 and tau plus 1. So that's why I have a tau plus 1 here, here's, you can look at it as e to the 2 pi I times 0 times k. So that's why I have a 1 here. Likewise, the blue tile in the middle, you can find it encoded here. So it gives rise to an exponential term here. So if you move to the next column, you see a 1 here because I have a red tile at position 0, and I have a blue tile at position tau. So that's how you get the Fourier matrix. So note that so this is no longer an abelian property. So if you change the ordering of the tiles within the rule, then you also change the matrix, which means that it captures more of the actual properties of the measures that arises from the tilings. So what we want to do now is to construct what we call cocycle out of this matrix. So what we do is, so now we have an analytic matrix valued function, which depends on the real parameter k, which I can derive directly from my substitution rule or from my inflation rule. So what I do is I define the nth level product or the nth level cocycle to be the product of b of k times b of lambda k times up until b of lambda to the n minus 1k. So this is also called the spectral cocycle so there are several works by Sasha Bufetov and Boris Solomiak. Actually, it already appeared in their paper in 2014, but they haven't called it the spectral cocycle yet. And they formally called it the spectral cocycle in their paper in 2020 in a very similar setting. So this is the cocycle, which is a finite product of matrices. And what you can do is you can look at the asymptotic growth rate of the norm of this matrix. So this asymptotic growth rate, this asymptotic exponential growth rate of the norm of these matrices is what we call the Lyapunov exponent. So again, what you do is you start with this matrix, you sample it along the sequence k times lambda to the n. And then for this cocycle, we consider its asymptotic exponential growth rate. So what you do, we take the norm of bn, you take the logarithm, and then you divide it by n and take the lim sup. And this Lyapunov exponent is the one that we're going to use to study or to look at the absolutely continuous component. So some comments. So first, this Lyapunov exponent always exists as a lim sup, but it might not exist as a limit. There are some examples for which it does, but for us, it's enough to look at the lim sup. Second, it depends on k. It depends on the value of k that you put in here. And there are examples for which you can find actual values of the exponent, but as we shall see later, we only need the upper bound for it. And if the upper bound gives us what we want, then we can use the result. But the idea is it measures exponential growth. So if you replace this, for example, by instead of having different matrices here, you replace this with the same copy of the same matrix, say m to the n. Then the Lyapunov exponent of that is just going to be the logarithm of the absolute value of the eigenvalue of the largest modulus. Here it's more tricky because this is not commutative, so you really have to look at the value for each parameter k. Okay, so now we now arrive to the result which relates the Lyapunov exponent that we constructed, or we can associate to an inflation rule, to the presence or absence of absolutely continuous diffraction. So this is a joint based on a joint work with Michael Bache and Franz Gehler. So if you have a substitution rule, so first in one dimension, if you have an inflation rule which is primitive, so primitive means that the matrix the substitution matrix is a primitive matrix, which has inflation multiplier lambda, and with Fourier matrix BK, if we have this non-degeneracy condition that the determinant of BK is not equivalently zero, so you only need it to be non-zero for 1K, for one real parameter, and then it's already satisfied. And moreover, if the Lyapunov exponent associated to the cocycle is bounded from above by log square root of lambda, so it's strictly bounded from above by log square root of lambda, for Lebesgue almost every parameter. So if this bound is satisfied for Lebesgue almost every K, then the diffraction does not contain an AC component. And this is a very technical result, but the point is, if this happens, the way you can prove it is, if this happens, if you have this bound for the Lyapunov exponent, and then you assume that you have a non-trivial AC component, then the Radon-Nikodym density associated to it will grow exponentially. And this exponential growth rate is not allowed for the systems we're looking at, because it's going to contradict some boundedness properties of the measure. So it means you have a minimum exponential growth rate, which is not compatible with the measured theoretic properties of the Radon-Nikodym density. So likewise, the contrapositive is that, okay, what if you have a non-trivial component? So if you have an inflation rule and you have this Fourier matrix as above, if a priori you know that you have a non-trivial AC component, then it must be that the Lyapunov exponent is equal to exactly log root lambda for a set of parameters of positive Lebesgue measure. Because otherwise you get this one. And actually, for the ones we know satisfies this condition, for ones we know have non-trivial AC parts, we can confirm that they actually satisfy this. In fact, for most of them, for all K. And then you have the higher dimensional example where you just replace lambda by the determinant of the expansive map. So now your inflation factor is no longer just a number, it's a map. It's a map in RD, which is expansive. So it has all of its eigenvalues have modulus greater than 1. And then you have a similar criteria for these rules. So in my last few minutes, I will try to go back to the two examples that we mentioned, namely the Fibonacci and the Godrej-Lauzon-Biard example. So the Fibonacci example, it has been long known before that it has pure point diffraction. So a priori, we know that it doesn't have an AC component. As a test of compatibility with this result, we can actually compute bounds for the Lyapunov exponent. So I'm not going to go through the detail of what this is, but these for each n gives an upper bound for the Lyapunov exponent for all parameters. Sorry, for almost all parameters. So if you know, if you're familiar with Kingman's additive ergodic theorem, these bounds are actually of Kingman type, or the ones you get from Kingman's theorem, Kingman's additive theorem. And the point here is that this bound is actually monotonic in n, monotonic and decreasing in n. So once you reach a bound which falls below the threshold, then you know that you satisfy the condition. And in this case, so this is the bound that we were trying to get below, or we want to get under this bound, which is 0.96. If you look at n is equal to 3, we're already at 0.8776. And so it means that we satisfy the bound, we don't have absolutely continuous component for the Fibonacci. So it's very, so the point here is that you can run numerics with your matrices, and actually the hard part in these kinds of results is that to show that these are the ones to compute numerically are actually true bounds. They're actually true bounds for the thing you're computing. So for this one. So if you go to the Goodrich-Lanson BR tiling, well, the Fourier matrix for this one is going to be larger. It's going to be 10 by 10 matrix. And now you live in R2. So, but you can still do the same. You can still do the same numerics for that. So this is the original paper by Goodrich and Lanson in 1992, where, so they already have theta here. So theta is actually square root of lambda for us. And they already said that it's not a piso number. Hence, this proves that proves the absence of Bragg peaks in the Fourier spectrum. So already in 1992, they already know that it doesn't have a pure point component. So the first component is already missing. But it's not clear to them what the continuous component is composed of. And they conjectured that, with reference to this paper by Goodrich and Luke, that any non-piso structure will have generically a singular continuous spectrum. But since 1992, no one was able to prove it, that it actually is the case for this example. And one corollary or one result which we can derive from that criterion is that it is actually true that this tiling or the diffraction coming out of his tiling doesn't have an SE component. So it's very important because that problem was posed in 1992, and since then there hasn't been an example of a higher dimensional tiling which doesn't have AC spectrum, apart from the ones which are pure point. So this is the first example of a two-dimensional tiling with singular continuous spectrum. So to summarize, so we have this rule that helps us generate tilings, and I told you that if you have a tiling, you can derive a point set from it, which is here what lambda is, which comes from just collapsing tiles into points. And that point set gives rise to a diffraction measure, which splits into three components: the pure point component, absolutely continuous component, and the singular continuous component. So from this rule, one can also combinatorially derive a Fourier matrix, which is now an analytic object. And then you can compute the Lyapunov exponent from this Fourier matrix. And the result which I have just told you is if this Fourier matrix is bounded from above by log root lambda for almost every parameter k, then you don't have this second component in the diffraction. So this is one criterion which allows one to exclude absolutely continuous components. So there are still lots of open questions regarding this. For example, it's still open whether if lambda is irrational, whether it can contain an absolutely continuous component. So every substitution we know for which this is non-trivial has lambda being an integer. So we don't know of an example yet where lambda is irrational and this is non-trivial. So that's one of the open questions. And of course, if lambda is piso, we will also like to check whether for all piso substitutions, this second component is missing, which is some sort of a weaker version of the piso substitution conjecture. But at the moment we still don't have a general approach to that problem. So I think I'll end with that. Thank you for your attention.
Thank you very much, Neil. I want to thank you, and I hope we'll thank you all. Well, we'll thank you all. And are there any questions for Neil?
I have a question. Thanks for the talk, Neil. Okay, so you were saying it's so the weak version is also no, the weak episode conjecture is also but my feeling is that the conjecture is open in general, but for concrete examples is usually you can find it, right? Or not.
Yes. Yes.
Uh-huh.
So I think so the piso substitution conjecture, I think so first of all, for two letters, if you have only have two letters, then it's known that it's always all true for all two letter substitutions which are piso and irreducible. This is a result by Frank Hollander and Boris Solomyak in 2003. There are also large families of examples for which people have shown that this is actually true. So I think Marcy Barge has a large class of families for which he confirmed that this is true. But
there's not a concrete example where the conjecture is not known, right?
No, there's no counterexample yet.
Yeah. No, not counterexample, but I mean a concrete example that is open.
That is not resolved. No, I don't think so. And it's the same for this Lyapunov exponent. So if you give me an example, I can confirm whether it's satisfied, whether it has no AC. So it's a sort of an algorithm in itself, but it doesn't give you a way to prove it for like a large class of families, unless the family is very simple, like constant length, for example.
And I guess for the singular continuous part, it's even more mysterious, right?
Oh yeah, definitely. Yeah.
So I did not understand the difference very well. Is there an intuitive way between the absolute continuous and singular continuous?
If you look for two immorts, for example, you know that you can see it from the autocorrelation coefficients. Because it doesn't decay to zero, so it can't be absolutely continuous. But it also doesn't give rise to pure point components. Maybe that's not the best answer, but so in general it's really difficult. There are more measure theoretic characterizations,
I see.
which are finer, like for example Nikolai Strangaru and Timo Spindler, they have results saying that if a measure is vanishing at infinity, then it has absolutely continuous Fourier transform, which is like the generalization of Riemann-Lebesgue lemma. But like if you're given a substitution and you're just given a measure, it's hard to split that into parts which you can try and use that result for. So
I see. Okay.
thank you.
Thank you. Are there any further questions? Or Neil?
So I have one more. Neil, do you know in substitution how continued fractions play a role?
Like if like the continued fraction expansion of lambda.
Uh-huh.
So this I don't think there's a. So for cotton project sets, it has a lot. It has, for example, for Sturmians, it has a more clear interpretation, namely that if lambda is a badly approximable number, then it has a clear interpretation for the corresponding cotton project set. But for substitutions, I don't think it plays a role that much. What's important is whether lambda is piso or non-piso.
Okay.
So if it's piso, then it's known that you have a non-trivial pure point component. So you have Bragg peaks. And if you're non-piso, then you can't have Bragg peaks. So it's an if and only if.
So Where do you say it plays a role?
Sorry?
So you mentioned an example where it does play a role.
Yeah, for so the Fibonacci point set that we have, I showed that it comes from a substitution, but you can also get it from a cotton project scheme. And for those, I think these Diophantine properties are more important. For example, yes. So I think Jamie Walton and Henna Koivusalo, they have recent papers on the relation of cotton project scheme being Diophantine to the corresponding point set having linear complexity.
Oh, cool.
So it's related to properties of the point set. So they have a definition of when a cotton project set is Diophantine. Yeah.
So what do you say, Walton? What?
Jamie Walton.
Jamie Walton. Okay, I'll write this. Okay.
Sorry, could you give us the title of the paper?
So it's by Jamie Walton and Henna Koivusalo. It should be cotton project sets with polytopic window complexity. Actually, they have two papers on it. First one is on complexity. So you're looking at patterns, and then you're looking at how many patterns of a certain size there are. And the second paper is on linear repetitivity.
Okay. Yeah, I'm already in Walton's webpage, and I think
I found it.
Yeah.
I found it, Pharaoh.
Oh, great. Thank you.
Sorry, I think it's in the second paper actually.
Okay.
Yeah, relating a Diophantine condition to a condition for linear repetitivity.
That's okay. Thanks for the reference.
No worries.
Well, I have a question. Oh yeah, I'm not silenced. Does the theory becomes easier when you deal rather with like some substitutions like the golden ratio or the Fibonacci substitution, if you work with like some morphisms, like I mean morphisms like working with K regular sequences, K automatic sequences and all this stuff.
Right. So if I go back to my first slide. So yeah, here, if you look at the Fibonacci substitution, the rule sends two letters to words of different lengths. But you can also consider a rule that sends A to AB and B goes to BA. So in that case, this geometry becomes very simple because each tile will be of length 1. All of them will be of length 1. So in the point set that you'll get if you do this process just sits on Z. So there's it simplifies a lot of the theory, but even for those, there are still open questions. So we call them constant length substitutions.
Yep.
Where letters are mapped to the same length, so words of same length, but there is still no complete characterization of their spectrum. The best known characterization is Decking's result, saying that if you have a coincidence, so for example, you have A goes to AB, B goes to AA, so you have a coincidence on the first column, then you have pure point spectrum. So a coincidence means that in one column, you see the same letter.
Yep.
And it's a dichotomy in a sense that if you don't see a coincidence, then you have mixed spectrum. But in a subclass where you don't see a coincidence, there's still no there's still no generic result on whether they're AC or SC. There are only a few sufficient conditions.
All right. Right, well,
And
thank you
of
very
course,
much.
those constant length substitutions, they correspond to the ones which generate automatic sequences.
Yes. But I don't know, I just kept me thinking. Well, I don't think I have any more questions. Felipe says that thank you very much, that I think he has to leave. Yep. So, well, I don't know if there are any further questions. Well, I just have a small reference request. Where can I read like about this like in a more calm manner?
So
Some of your papers regarding this, or
so I would suggest this paper by Michael Backe, Franz Geller, and myself.
Yep.
In 2019, which I think we published it in CMP, Communications and Mathematical Physics.
Yep.
There should be a link in my website. Otherwise, I'll be glad to send you the link.
Okay, thank you very much. I'll just look it up because it seemed quite interesting.
Thank you.
Well, I don't know if there are any further questions to Neil. Well, if there are no further questions, let's just give him a virtual applause and thank him. And just before everyone leaves, I'll tell you that next week at the same hour, we have Karma Dejani with us. Also, Neil, you're very welcome to attend if you want. It's at the same time right now. I think it's right now it's 6 in the evening, right? In Germany.
Yes, yeah.
Yeah, so it's 6 in the evening in Germany, 10 in the morning in Mexico. Well, most of Mexico. Right. Well, then
Going towards lunch.
Thank you very much for your talk again. And